who will tell us about bridging quantum thermodynamics, gauge theories, and quantum simulation.
Awesome.
Do you know how the slides appear?
I think they're supposed to already be there. Awesome.
Yeah, please take it away.
Thank you. Thanks for the introduction. My name is Greeshma Oruganti. I'm a PhD student at the University of Maryland, College Park. It is a pleasure to present the work that I did with my collaborators. The talk is based on a preprint and an article that we just published. This is going to be today's dose of high-energy physics for you. The title of my talk is Bridging Quantum Thermodynamics, Gauge Theories, and Quantum Simulation. The three fields, quantum simulation, quantum thermodynamics, and gauge theory, seem unrelated at the face of it, as we heard yesterday. But these fields are related, and they also offer insight into each other. Quantum thermodynamics, we know, is the extension of macroscopic laws of thermodynamics to the quantum realm. And no process, including quantum simulation and quantum error correction, can violate the second law of thermodynamics. There's been interesting work done at the intersection of quantum thermodynamics and quantum simulation. Some examples include the thermodynamic cost of error correction and how to cool a qubit using quantum refrigeration. On the other hand, as we've heard yesterday, quantum simulation offers us a way to probe fundamental particles, fields, and their interactions. We can now study non-equilibrium phenomena in high-energy physics, such as string breaking and scattering. For the very first time, we believe that we bridge the fields of quantum thermodynamics and lattice gauge theories by demonstrating how to compute thermodynamic quantities for lattice gauge theory. Along the way, we also discovered a relationship between quantum information and quantum thermodynamics that potentially allows us to verify a framework on a quantum simulator. The talk is approximately divided into three parts. In the first part, I'll introduce what strong coupling quantum thermodynamics is and how it's related to quantum information science. In the second part, we'll focus on experimentally realizable sudden quench processes. And when a strongly coupled system undergoes such a process, I'll tell you how to define work and heat, and we'll see if they satisfy the second law of thermodynamics. In the third part, I'll apply this entire thermodynamic framework to a Z2 lattice gauge theory, in which we'll see exciting implications for quantum simulation. Let's begin with the first part. The standard thermodynamic setup always involves a system whose Hamiltonian is H sub s, a reservoir whose Hamiltonian is H sub r, and the interactions between the system and the reservoir are denoted by V sub s union r. So total Hamiltonian is simply a sum of these three terms. The general state of S union R is denoted by rho sub S union R, and to obtain the general state of the system, we trace out the reservoir degrees of freedom to obtain rho sub S. The equilibrium state of S union R at some temperature beta inverse is denoted by pi sub S union R. It's simply the Gibbs state under the total Hamiltonian H sub S union R, and Z here is the partition function or normalization factor. Again, to obtain the equilibrium state of the system, we trace out the reservoir degrees of freedom from pi sub S union R to obtain pi sub S. It's important to note that pi sub S is not necessarily a Gibbs state under H sub S under all conditions. And to understand why that's the case, let's talk a little bit about weak coupling and strong coupling quantum thermodynamics. In weak coupling thermodynamics, which is often what we were introduced to in standard textbook thermodynamics, it's common to neglect the interaction term. So in such situations, the internal energy is simply an expectation value of H sub s, and the equilibrium state is simply the Gibbs state under H sub s. On the other hand, when the expectation value of this interaction term is at least comparable to the expectation value of H sub s, we can no longer ignore these interactions while formulating the thermodynamics of the system. And so in such situations, internal energy is no longer just the expectation value of H sub s. The equilibrium state is not just the the Gibbs state under H sub s, because in both these situations, we need to account for the interactions. Strong coupling thermodynamics has been well studied for classical systems, and in our work, we extend this to the quantum realm. I said before that pi sub s is not a Gibbs state under H sub s, but it can be written down to look like a Gibbs state under this new operator Hs star. Hs star, also known as the Hamiltonian of mean force, is defined as -1 over beta times log of the ratio you see on the screen. This modified system Hamiltonian captures the effects of the interaction on the equilibrium state of the system. Because this operator doubles as an effective energy operator on the system's degrees of freedom, it's natural to define the internal energy as an expectation value of this operator in a given state rho sub s. This definition of internal energy is valid for both equilibrium as well as non-equilibrium states of the system, but it's measured solely on the system's degrees of freedom. Using this operator, we can define other thermodynamic quantities, such as the free energy F sub s, which equals -1/beta times log of the partition function, where the partition function now depends on the Hamiltonian of mean force. With this choice of internal energy and free energy, we can use the standard thermodynamic relationship, where free energy equals internal energy minus beta inverse times the entropy to define the entropy of the system. And doing some algebra, the entropy of an equilibrium state of the system turns out to be the von Neumann entropy in that state. Given all of these key thermodynamic quantities, the question is, can we measure any of these quantities experimentally? The Hamiltonian of mean force consists of logs and partial traces. We potentially can't expect to measure this operator in a quantum simulator. What we can measure instead is this quantity called the entanglement Hamiltonian, which is defined as minus log of the reduced density matrix of the system rho sub s. We discovered that I must say, this object, the entanglement Hamiltonian, has been well studied in literature on both condensed matter as well as quantum information science. It's been used to characterize topological order, a tool to investigate thermalization in gauge theories, and is widely used in quantum state tomography. And we discovered that this object, the entanglement Hamiltonian, is related to the Hamiltonian of mean force when we're in equilibrium via the simple relationship where the Hamiltonian of mean force equals 1/beta times the entanglement Hamiltonian plus the free energy of the system F sub s. It's not often that we want to measure the free energy of the system, but rather we want to measure the changes in the free energy of the system. And so to talk about changes in these thermodynamic quantities, let's focus on some thermodynamic processes. Here, like I said, I'll introduce what sudden quench processes are, where the Hamiltonian changes abruptly. And when the strongly coupled system undergoes such a process, I'll define work and heat. And we'll see if these definitions satisfy the first two laws of thermodynamics. We always begin our process in a global equilibrium state, pi sub s union Ri, under the initial Hamiltonian h sub s union Ri. At t equals 0, we instantaneously change the total Hamiltonian from hs union Ri to hs union Rf. At a time slightly after 0, we have this new Hamiltonian, but the state of s union R and consequently the system have not changed due to sudden approximation. From 0 plus all the way to the final time, we let s union R evolve under this final Hamiltonian until the system evolves to its final state, rho sub s f. There are two stages in this process. The first is around t equals 0, where the Hamiltonian changes, but the state of the system remains the same. And so the change in internal energy solely due to the change in the Hamiltonian is what we refer to as work. And in the second stage, from 0 plus all the way to the final time, t sub f, the Hamiltonian remains fixed, but the state of the system changes. And so the change in internal energy solely due to the change in the state of the system is what we refer to as heat Q. And by construction, the first law of thermodynamics is satisfied. For this entire process, we can also define what the change in free energy delta F sub s is, and we analytically prove that W is greater than or equal to delta F sub s for this process, which is the statement of the second law. And if the system were to end up in a final equilibrium state, we can restate the second law in terms of heat and change in entropy as Q is less than or equal to beta inverse times delta S. The question now is, can we measure any of these thermodynamic quantities using the previous relationship between the entanglement Hamiltonian and the Hamiltonian of mean force? On substituting this relationship into our definition of work, we obtain the third equation, where work equals the difference in the expectation value of the entanglement Hamiltonian plus the change in free energy delta F sub s. Often measuring delta F sub s can be extremely expensive, either because we have a large number of degrees of freedom in the reservoir, or these degrees of freedom are simply inaccessible. And so instead, we can measure this quantity called the dissipated work, W sub dis, which is the difference in work and the change in free energy, which now is expressed only in terms of the difference in the expectation value of the entanglement Hamiltonian. And so to verify the second law, it is sufficient to measure dissipated work and make sure that it's greater than or equal to 0. And this connection between quantum thermodynamics and quantum information science potentially allows us to verify our thermodynamic formulation on a quantum simulator. This brings me to the last part of the talk, where I'll apply the thermodynamic setup to a gauge theory. I'll introduce what gauge theories are, and then we'll talk about its thermodynamics. As we've heard yesterday, gauge theories, lattice gauge theories specifically, are obtained by discretizing space and time in quantum chromodynamics theories, and so they allow us to study QCD non-perturbatively. Hamiltonian formulations of lattice gauge theories are best suited for quantum simulation experiments, but these formulations are inherently redundant. To remove these redundancies, one imposes local constraints called Gauss's laws, and these are explicitly implemented in Hamiltonian formulations. From electrodynamics, we know that the Gauss law states that the electric field flux coming out of a surface is proportional to the charge enclosed by it. We use this as well as boundary conditions to fix the gauge in electrodynamics. That's exactly what we do in lattice gauge theories by using Gauss's laws. This entire process can be visualized in terms of the Hilbert space, where the Hilbert space is split into two parts, and all the states that constitute the physical Hilbert space must satisfy these local Gauss law constraints. One way to restrict the dynamics to this physical subspace is to penalize transitions to other excited states or other unphysical states. And in doing so, we end up with a large interaction term. And we know that a large interaction term implies that strong coupling quantum thermodynamics forms the appropriate framework to discuss the thermodynamics of lattice gauge theories. I must mention that previous works of lattice gauge theories involve computing thermodynamic quantities for equilibrium systems or not in the framework of quantum thermodynamics setup. So we now apply our previous thermodynamic formulation to this Z2 1+1 dimensional gauge theory, which is coupled to spin-half hardcore bosons. We have 6 lattice sites in the total system, and the subsystem of interest on which we intend to define the thermodynamic quantities is labeled by S, called the system, which consists of 4 lattice points colored in pink, where spin-half particles exist, and the other 2 lattice points colored in green belong to the reservoir. Again, spin-half particles exist there. These are connected via links on which more particles live. And this entire S union R composite is described by the total Hamiltonian. The total Hamiltonian consists of 4 types of terms. The first is the matter hopping term, which tells us that when a particle hops from one lattice site to another, the spin on the link flips its sign. The gauge field terms are the electric field terms proportional to the lattice, the links. The staggered mass terms act on the lattice sites and are again proportional to the number of particles on the lattice site because the sigma plus sigma minus operator, m is the mass of the boson. And the chemical potential terms similarly act on the lattice sites, mu is the strength of the chemical potential term. We now subject this entire S union R to a system's chemical potential quench. By that, I mean the system's Hamiltonian consists of 4 types of terms, and we just changed the chemical potential terms of the system by changing the value of mu from its initial value of 0 to a final value of mu sub f, exactly at t equals 0. This constitutes our chemical potential quench for the system. For this process, we compute dissipated work, W minus delta F sub S, and we plot it as a function of the final quench parameter mu sub F. And we see that dissipated work always lies above 0, indicating that W is always greater than or equal to delta F sub S for this process, which verifies our analytical results. At a point that I've labeled mu sub Fc, the behavior of dissipated work drastically is changing, and to investigate this further, we overlay this plot with that of an order parameter called the chiral condensate. Chiral condensate, denoted by sigma, has an expression shown over there. And we know that the value of chiral condensate is different in different chiral phases of the theory. And here, chiral condensate is again plotted as the final quench parameter, where we see that sigma changes its value from a negative value to 0 exactly at the same time that dissipated work does. And this plot qualitatively indicates that thermodynamic quantities are able to signal chiral phase transitions in this theory. This brings me to the end of the talk. I've defined what key thermodynamic quantities, such as internal energy, entropy, and free energy for a strongly coupled open quantum system. When the system undergoes a sudden quench process, I define what work and heat are in a way that they satisfy the first 2 laws of thermodynamics. I also introduced a bridge between quantum thermodynamics and quantum information science that potentially allows us to verify a framework on a quantum simulator. I also motivated why lattice gauge theory should be cast in the language of strong coupling quantum thermodynamics. And we applied the thermodynamic formulation to a gauge theory. We found that thermodynamic quantities qualitatively signal the phase transition in this 1 + 1 dimensional Z2 gauge theory. Looking forward, we actually would like to measure these thermodynamic quantities, such as work and heat, on a quantum simulator for the lattice gauge theory. For this entire talk, I focused on just sudden quench processes, but the next natural question to ask is, can I extend this framework to other non-quench diabatic processes so I can study other non-equilibrium phenomena in high-energy physics, such as scattering or string breaking? I'd like to acknowledge my wonderful collaborators, Zara Dawoodi, my advisor Chris Jarzynski, Nicholas Miller, Connor Powers, and Nicole Younger-Halpern. Connor was the force behind the numerical calculations. I'd like to acknowledge my funding sources. And finally, thank you all so much for your attention. I'm happy to take questions.
We have time for a couple of questions. Yeah.
Thank you very much for the talk. I want to ask a question. How much of the derivations you presented in the first part of the talk depend on the fact that overall system is in Gibbs state? Or would it work if we consider some general types of states and just do this parameterization with defining this Hamiltonian of the mean force?
Yeah, that's a really good question. I think to talk about the second law, we need a temperature scale or an energy scale to set that. We begin in a global equilibrium state. And once we do that, just to talk about work and change in free energy, we don't need to end up in an equilibrium state. And our thermodynamic formulation is perfectly valid.
Yeah, but overall system can be in pure state, right? So, and we can define this temperature by just some local energy, right?
Potentially, but for non-equilibrium states, I'm not entirely sure what my definition of temperature would be. And that's really the problem. Thanks.
We could take one more quick question.
I'm here. Okay.
Yeah.
Nice talk. So there's the second law that you showed that was just an average, like expectation value of W, right?
Exactly.
Do fluctuation theorems apply here? Like, can you say something about the fluctuations of work?
Yeah, that's a good question. If my system is closed and I do my two-point measurement scheme, and I can come up with the fluctuation theorem, and fluctuation theorems directly imply the inequalities that I presented. But if I can say nothing about S union R as a whole, and all I'm interested in this is in the system's dynamics, then I can't use fluctuation theorems.
Okay, thanks.
Great. Okay, let's thank Greeshma again.
Thank you.